This is sort of the typical probe. It sticks out of the plane. Right here is the ice detector. So there's two optical beams that shoot across this gap. When ice builds up on this beam, it obstructs it, detects the ice. This is your typical pitot tube. And then this is a port where the air gets sucked in. So this is how it samples relative humidity. Inside every probe, there's 3 relative humidity sensors. So this is one of the trickiest things to observe is relative humidity because it's highly variable. So this is what the relative humidity sensor actually looks like. It's just a tiny little sensor. There's 3 of them in each probe, and these are the metrics that it collects. This particular plane is based in the UK. It's off the Flybe fleet. This other plane I included up here because I thought the paint job was cool. It's a 757 from Iceland Air painted as the Aurora.
Can I ask a question? Some of the people in here are also in aviation meteorology. Do you know in the 1990s why there was the push for the icing detector? Was there a specific crash or something?
Despite turbulence being the scariest thing, most aviation incidents are icing related.
Especially general aviation.
Right. And so I've got some cases at the end of this, including the Ted Stevens incident and the Colgan crash, which we have some interesting data from. So this is a screen capture of some software that we use to track the airlines and record the weather data. So this is kind of jumbled here because there's a lot of planes with sensors flying. But you can see the different, so we record 2 altitudes. There's a GPS altitude and a pressure altitude. Then there's the indicated airspeed. And then we have the meteorological data. So we have the wind, turbulence, icing, temperature, and relative humidity. And unlike accelerometer data, the turbulence that we observe is eddy dissipation rate. We also have a UAV version. So this particular version is about this big. It's manufactured on a 3D printer, sintered nylon basically. And this, to give you an idea, this is the iridium antenna. It's about the size of an iPhone. The cool thing about this is you can actually fly these things into places where you probably wouldn't normally fly a commercial airplane. So these are some flight tests that we did out of a naval research base right here in Pax River. And so we were testing UAV flight tracks. So when you're collecting data off commercial airlines, you collect data where they want to fly. You don't have a choice. With a UAV, you can actually determine the flight path. So the idea was, is there an optimal flight path to collect data? Well, it turns out there is, because the wind data, to derive an accurate wind measurement, you have to have an accurate heading. And it's hard to obtain an accurate heading if you're averaging over time while the plane's turning. So if the plane is making too tight of a radius, in other words, flying in a really tight circle like this, almost all the wind data is useless. So we were doing tests to determine what sort of roll angle and banking do we have with the wind data. And we also noticed some interesting profiles. So I'm sure everyone here is used to reading skew plots, so this is how we view aircraft data. These are the profiles. We have temperature and dew point for 2 different flights corresponding to those 2 different flight routes over there. They're different because they're 2 different days. The flight time is an ascent and a descent over the course of a couple hours. But what we see here are 2 things. There's a lot of noise down here in the bottom, and then there's this sawtooth pattern up here. And what we're seeing is the plane is actually flying in a circle, and half the time it's in the circle it has a headwind, and half the time it has a tailwind. And so you're seeing that the difference in the temperature and dew point is actually frictional heating impact on the probe. And so there's algorithms that we implement to back that out. So if we back up for a second and just talk in general terms, how much does aircraft data contribute to forecast skill in the model? So I've got a couple of plots up here from different government Met centers. This one is from the European Center, the ECMWF global model, but this is just the impact over North America. Now obviously if I was to show you the impact over the globe, AMS UGA would probably be on the other side of the door. If I showed you the northern hemisphere, it may be fairly tied with aircraft data, but just over North America, aircraft data has a massive impact. Same goes for U.S. impact. This is a model run by the Navy. MedCars is an actual form of aircraft data, so that's the U.S.-based wind and temperature off the flight management system. And then we see the same thing here. So this is INCEPT's, the impact. This is per observation. Aircraft data and radiosondes dominate the analysis. So if you actually look at what they call the output from an FSO, which is a forecast sensitivity to observation study, on a per observation basis, the top 3 contributors are radiosondes, aircraft data, and buoys. And it's primarily because they're sampling in situ data where there's really no other observing systems to do it. So if we're able to replicate what a radiosonde collects, and we can sample airspace where they're not launching radiosondes, the big hurdle in numerical weather prediction largely is that if the radiosondes are the dominant observing system in the models, but they only launch twice a day. So there's a 12-hour gap of no radiosonde. And then there's only a handful of locations where they launch it. And that was okay back when you cycled the model twice a day, and the grid spacing was 2.5 degree resolution. But now we're talking about running global models on a sub 10 kilometer grids and potentially cycling them more frequent than every 6 hours. The lack of radiosonde data is a real problem. And you can't just go launching more radiosondes into the atmosphere because it's a one-time use instrument, and it also interferes with air traffic. So the optimum solution is put that type of sensor on the airplane. But how do you know it's good data? Because the only thing worse than not having data to initialize a model is initializing a model with bad data. So quality control is probably the most important thing in numerical weather prediction as it comes to observations. So the way the system works is that the sensors are on the planes. It relays the data through a SATCOM system, so it works anywhere on the planet. There's absolutely no ground-based infrastructure needed to run the data. It goes from the plane to the satellite to our data center, which makes it kind of interesting because we've been pulling vertical profiles from airports in Cuba off Aeromexico Connect planes, even though we don't have any ground-based infrastructure anywhere near Cuba. So it goes into this real-time quality control filtering system, and I'll show you with the process that happens here in a second. So the first thing it does is it does buddy checking against co-located observations. So other aircraft data, then maybe the plane flew by a radiosonde and compares with that. Maybe it compares with some GPS RO data. That all happens in this database. And there's software that interfaces with the database that looks at the co-location statistics. If there's no co-located observations, then we use what's called an observation minus background metric. So that's, you essentially take your first guess of your model, and you take your observation, and you look at how much the difference is. That's what they call the OMP. If that diverges by too much, it doesn't necessarily mean the observation is bad. It could mean that the model background is bad. But if you see an aircraft that constantly has OMB statistics that are larger than other neighboring aircrafts, no matter where it flies, then it alerts someone on our staff who actually goes and looks at the history of the aircraft and the data to determine, is there something wrong with the sensor, or does this pilot just keep flying into storms that all the other pilots are flying around? And if they do find a problem, it's just a simple task of someone on the ground just unscrews 2 bolts, they swap out the little sensor board, insert a new calibrated board. Each sensor board has individual calibration constants unique to that board. So all the mechanic has to do is type in the serial number of that board, and we can use the SATCOM system to uplink the calibration constants to the probe. Then we start checking it, and if it reports good data, it gets assimilated into the models. So this is an example of 2 different flights with what we have. Red, obviously bad, something's wrong. It's good that we don't see any red here. blue is banking. So if we see a blue observation, that means the plane's entering some kind of turn. That means the wind data is flagged, but the temperature and the humidity data is fine. Green's good, all data is fine to use. Purple is when the probe actually accumulates ice, it has to de-ice itself. So it has internal heaters that'll de-ice itself. But the problem with that is when the heaters fire up, it invalidates the temperature and relative humidity reading. So purple means you don't want to use temperature, relative humidity, but the wind data is still fine. So what we see here, this is pressure altitude. So this plane takes off, lands. You can see right here, right after takeoff, it was probably doing a turn. Right here, when it sets up for final approach, it does a couple turns. Other than that, the data's fine. Same thing happens here. Typically what will happen is anytime they change a flight level, they do a turn, level off, turn, set up for final approach. What we see here is the plane actually flying into icing conditions. So this is positive icing. And so here we have, these are the actual temperature measurements from these flights. You know, obviously as they climb, temperature goes down, temperature drops, all of a sudden the heater's activated. And the heater stays on. So this is flagged because you don't want to use this data during your data assimilation process. This is rule number one, is read the manual. So I love my friends at the UK Met Office, but they didn't read the manual. And they showed me this Gaussian distribution of temperature error, which was bimodal and had a second peak around plus 10C. And they said, we don't know what's going on here. And I said, are you withholding the icing flag data on temperature? And they looked at me like they didn't know what I was talking about. So this was actually before we had 3 relative humidity sensors. The first version of this had 2 relative humidity sensors. So this is what happens when RH1 and RH2 agree with each other. You get this nice, even distribution. Typically, you'll get 3 reported values, RH1, RH2, and the mean between them. This is what happens when RH2 starts to fail. So this is the data when, and it'll typically fail in a more moist environment. We see some sort of distribution that's skewed one way or the other. And we notice RH2 gets flagged, so then the user still has a choice of using RH1 or just not using them at all. The new sensors actually have 3, so there's a tiebreaker, because sometimes you will have a very good correlation, but it'll still be some spread. And so the third one was essentially the tiebreaker. So now we take it to the next step where we actually co-locate with other observing systems as well as a short-range model. So we'll run a model out just a couple hours and compare that with model predicted values. And we can also do this with the first guess, which is the model background. So here we have radiosondes, ACARs, and TAMDAR. And on the top, we have temperature, and on the bottom, we have relative humidity. And on the axes here, these are the observations, and these are what the model was expecting. So in general, it doesn't necessarily mean this observation is bad. It just means the model thought it was supposed to be down here. You get a pretty decent distribution. The point of this being 2 ways. This is one way to verify the accuracy of the data, but it's also a way to verify or quality control it. So we get these quality control flags. So QC, obviously, black here in the middle is good. As you get further away, it gets flagged. Doesn't necessarily mean it's bad again. It just means that it disagrees with the model. And we see the same thing for the U wind and the V wind. And this is a little bit more granular distribution where we actually divided the quality control flags up into 9, 10, 7, 8, 5, 6. So for our data assimilation systems that we run internally, we only assimilate data with QC flags of 9 or 10. To give you an idea of the distribution, the majority of the data are 8, 9, or 10. So the stuff that fails the QC is pretty infrequent. So it's pretty reliable data, but you can't take my word for it. NOAA's got to prove it to themselves, and I don't blame them. So the FAA actually funded NOAA to do impact studies and data quality assessment for 4 years because they didn't think one season was enough. They wanted to see 4 years worth of continuous data. So this was a major field experiment where we actually did all sorts of tests with the University of Wisconsin, what they refer to as their Arabago, which is a RV equipped with all sorts of cool instrumentation. And we would go out and launch high-resolution GPS-equipped radiosondes behind the planes, not in front of them, as they take off from the runway. And we do these co-located experiments. So you can actually see here, so these dotted lines are descents of planes coming into the airport. Most of this was done at Memphis. These solid lines are planes taking off, and the green lines are the radiosonde launches. So the first thing when we were sort of putting together aircraft data in SKU plots, and the National Weather Service Office was actually looking on AWIPS at the SKU plots, we had to put together sort of a training module. So a guy by the name of Rich Mamrosh, who I don't know if he still is, but he used to be the SKU at Green Bay, put together this fantastic tutorial on how to use a SKU for an aircraft, because it's intuitive when you look at a vertical profile from a radiosonde because it goes straight up. But if you look at a SKU from a plane that comes in from one side and a plane that takes off and goes that way, you could get two SKUs 5 minutes apart that say something completely different. And the forecasters panic. They're like, what's going on? You know, these planes were 5 minutes apart. How come the data doesn't match up? So instead of having a photograph on the top, we actually have a trajectory of the flights so that they can say, hey, okay, now I understand what's going on in the atmosphere. This plane came in from over here and it went out that way. So INCEP started assimilating the data into several different models. This is output from the GFS. And they actually were looking at the biases. Of course, this is respect to the first guess. So this is basically your O minus B statistics. TAMDAR, ACARS, and radiosondes. And I think the big shocker here for everyone was this massive bias that the radiosondes had above 400 millibars. Until there was an actual co-located in situ data set out there, there was really nothing to determine this. So we always use radiosondes as sort of verification. That's the gold standard. That's the benchmark for truth. But you know, it's hard to say if it's right or wrong if you assume it's true. And you don't want to necessarily bias correct your observing system to another observing system, because if it turns out if that observing system has its own biases, you might have just made yours worse. So these are the results of that 4-year impact study. If you want to read more, the primary paper is by Bill Moninger in Weather and Forecasting, 2010. There's the secondary paper by Stan Benjamin in Monthly Weather Review that talks about the same stuff. And then Bill Moninger actually uncovered a very, very interesting problem in aircraft data. And I'll explain how we fix that in a second. So the third paper here is a paper that I wrote that talks about how to fix the problem that Bill uncovered during the study. So the way this study was constructed was there was 5 different models, and each model had a control version of itself. So essentially, it's sort of like a clinical trial. You run 2 parallel versions of the model. Everything's equal, except the experimental model has the TAMDAR data added to it. Presumably, if the addition of the TAMDAR data improves the forecast skill, then that model will verify better, which it does. So what we see here is forecast skill improvement as a percentage. These look like big numbers, but you got to think, if your forecast error is 1 degree and you make a 0.5 improvement in degrees, that's a 50% improvement. You're only improving at half a degree, but it's 50%. So in general, we see 20 to 30% improvement using the top 3 models, and between a 40 and 60% improvement using the bottom 2. The difference between those is these 3 use 3-dimensional data assimilation, and these 2 use 4-dimensional data assimilation. And aircraft data is very asynoptic. It's a 4-dimensional observing system, really. And the 3-dimensional data assimilation systems sort of lose a lot of the impact of the observations as they move further away from the analysis period. You can kind of mitigate that by doing a rapid cycling model, so you just shorten that window that you've been your observations. But the best way to do it is just vary time in the equation, because that makes the most sense. That way all the observations have equal influence. And so this is a time series of the output. And so this is actually this plot right here sort of goes back to what I was saying. So the blue model here is what they call the dev. So this was the control model. And the dev 2, the red model, is the experimental model, which is identical to the control, except it had the TAMDAR data in it. And this is the difference between the 2. So this is the analysis. This is the control model. This is the experimental. And you can see the maximum potential impact there is roughly 45%, which is a pretty large improvement in forecast skill, because when this study was conducted, it was just using 1 fleet of planes. In fact, here's a time series between these 2 difference of the model here. And right around April 2008, we turned on the switch to pipe NOAA data from 40 Chautauqua ERJs, which are, regional jets, kinds that have, 1 seat on one side and 2 on the other, and they're really tiny. Just 40 planes. And look how much the skill in the model jumped up, almost instantaneously. So here's another study, because one thing that we found was that there's more than just a direct improvement from the data influence. You can actually improve the other observing systems. So here we have the run with the TAMDAR data. Here's the run without the TAMDAR data. And we expected to see this kind of impact, because this is actually this is verified just over North America, so the in situ data is going to have more impact than the satellite data. It's just a numbers game. We have a lot more observations in space and time than any other observing system. We also expected that the impact of AirEP, which is the top, so that's your typical ACARS wind intent, we expected that to go down in this run, which it did. And the other thing that was actually kind of surprising was that the AMS-UA impact went up in this run, as well as the atmospheric motion vector impact went up. And what you're seeing here is the TAMDAR improving the analysis. It improves the first guess in one run, and a better first guess in the next run actually allows that run to accept or reject other data sets more intelligently. So here we have some vertical profiles of statistics. The top row is ECMWF's analysis. The bottom row is INCEP's analysis. So this is all done in their global models. This particular column is temperature. This particular column is wind. And this particular column is humidity. Well, this is RH, and this is actually mixing ratio, but moisture. And in general, you can see that the trends are pretty similar between the 2 centers. So we've got the dotted line centered around 0, our bias, and then the air is out here to the right. In this case, solid lines. In this case, just the black lines. And we have comparisons with TAMDAR, AMDAR, radiosondes, and in case of ECMWF, their analysis. What the government med centers wanted to prove to themselves was, is TAMDAR at least as accurate as a radiosonde? So for climatological purposes, no one's going to discontinue launching radiosondes. But if they have a couple of radiosonde launches, and one happens to be co-located near an airport, which is pulling in a lot of aircraft data, they don't need to have a lot of high-density radiosonde sites for the climatology. So they can actually save some money by swapping out the profiles. But the concern was, would it have the same impact in the model? Is the data quality the same? In general, the answer is yes. We actually conducted our own test internally using a WRF-based solution. We followed the methodology outlined in O'Carroll, and this is the paper that is a weather and forecasting paper. So you can actually get the reference to that in here. It's a way to do a three-way co-located study. So the three ways co-located were the TAMDAR, the radiosondes, and a short-term model forecast. And over here we have January, and then we have June. So we have, in general, performing equivalent to the radiosondes. In some cases, actually performing better than the radiosondes. So this is a plot out of Moninger et al.'s paper on the TAMDAR impact. And so this is AMDAR data. So the difference between AMDAR and TAMDAR is AMDAR's wind off wide-body major airlines, and the TAMDAR is a wind off the regionals. The interesting thing about the TAMDAR is the regionals are flying into smaller airports, they're making more flights, so you're actually getting data in the boundary layer where you really want it. There's nothing wrong with the AMDAR data, but if you're getting that off, an LAX to Heathrow flight that makes that flight once a day, you get two profiles, and all the other AMDAR data is around 250 millibars, which is nice, but it doesn't really help the model, which really needs stuff probably below 20,000 feet. So there was this, obviously, a big problem here. Something's wrong with the wind, because we're looking at RMS wind air with respect to the model, and it should be lining up with AMDAR, but it's not. There's a problem. So the hypothesis was, and this is true, it's off the heading. The problem was when you derive a wind vector from an aircraft system, you have to have the ground track of the plane, the direction that the plane's pointed in, because if the plane's trying to fly this way and there's a strong wind coming from this way, it's actually going to point this way, but move kind of like that. So there's two different angles. So this is why it's tricky to get accurate wind data from a plane versus a radiosonde. You launch a radiosonde, it's going to go wherever the wind blows. It's a direct observation. Aircraft wind is actually a derived value, and it's derived from two variables. It's derived from speed and direction. The problem was the heading on these planes had major biases, and I mean major. So I don't understand. There was planes in Alaska with greater than 10-degree biases. How they found the airport when they flew, I have no idea. The problem is you can't derive accurate wind data from a plane with bad heading. So here's how the calculation actually works. So we've got this vector here, which is called the wind. This is the TAMDAR observed wind. And it's calculated from the ground track of the plane and the air track, basically. So we've got, this is the way the plane flew. This is the actual ground that it covered. The difference is the wind vector. And then, of course, this has an associated angle with it. Then we go into a model or a co-located observation at the same space-time, and we pull out a wind vector from the model. So let's say this plane calculated this wind vector at a certain latitude and longitude and altitude. We go into a model, and we pull out the wind vector from that same latitude, longitude, and altitude, which is this W ref here. This is the reference wind. And we use the ground track vector from the plane, and we calculate a theoretical air track. Okay, so now we can compare two things. We can compare the difference, the angular difference between the air track reported by the plane and the theoretical air track as expected by the reference wind from the forecast model. This is your error in your heading. If you make the assumption that the model is perfect. Of course, no model is perfect, but if you watch this, if you do this calculation day in and day out for every observation over the course of 12 months, you'll eventually get rid of the noise. So, where did we get this idea from? I had to go way, way back to a way that they actually calibrate heading instrumentation on ships. There's kind of an interesting story behind this, because I knew that this equation existed, but I didn't know how it was derived. And no library has this paper, except for the library at the Naval Observatory. And it just so happened that one day I was at a meeting at the Naval Observatory, and I had an extra hour or two to kill after the meeting. So I went to the library, and I talked to the librarian, and I said, I'm interested in this paper. These are the journals. And she's like, we have those, like original copies. So puts on the white gloves, pulls it out, and scans it for me. And this is actually, it's hard to tell, this is actually a picture of one of the scans that she sent me with this equation. So here is the actual equation that we used. The prime being the theoretical value in that earlier plot. The issue with this is that there's what they call a small angle assumption. So there was a lot of hand waving on the page in front of this, because empirically, the sailors know that this is how you calibrate heading. And they started with equations originally listed in this paper here. And they knew if they started with equations in here, and they were supposed to end up with this because they knew this is the way to fix it, they tried to derive it. But they got to a point in their derivation where they couldn't get these terms to cancel out. So there was some hand waving, and they skipped a step. So I wrote the paper after we did the study. I sent it to JTech, the Journal of Atmosphere and Ocean Technology, and it was accepted, but one of the reviewers said, I'm having trouble with this, and in the appendix was derivation. They said, I'm having trouble, I can't get from equation 15 to 16 or whatever it was. And I was like, oh man, this is that step that they glazed over in this paper. It turns out that you can get the terms to cancel out if you make a small angle assumption. So if you assume that the angle is small, that ends up meaning that, you have like a cosine of 0 and a sine, it ends up with like 1s and 0s, and the 0s cancel out the terms. It took me about 6 months to figure it out, and then I sent it back to the editors, sent it back to the reviewers, and so now the correct derivation to this paper that came out in the 1800s is in the appendix of that paper. And no one else on the planet will probably ever need to read it or learn it. But it actually, the point of me showing this is to sort of illustrate the importance of the publication process. Because had this not been published somewhere, we would have been scratching our heads. Because I wouldn't have thought of this off the top of my head. So they were geniuses back then. They didn't realize it would still be useful. So this is what data looks like if you collect it for 12 months. So here we have the air track heading, and here we have degrees from north. So it runs 0 to 360. And these are all the different comparisons. So if the data off the plane was perfect, you would just have basically a straight line going from 0 across you. It turns out that there's always, when in a compass bias, there's going to be some type of sinusoidal signal. And so here we have 3 references. We have the rapid refresh, RTF-DDA WRF, and ICARS data. And over here we just have the RAP and RTF-DDA. So these are 2 different planes. And every plane's heading instrumentation has a unique bias characteristic. So the first thing we had to do was identify the tail number, calculate the bias on a per tail number basis. And then it was a simple solution. All we do is we do a best fit sinusoidal curve through here, and then run the raw observations through the inverse of that curve, and the error goes away. So here's a before and after plot. These two lines over here, look how much the error is in knots. I mean, we're talking wind to air exceeding 40 knots. I mean, this error is greater than some wind observations themselves. And we have the transverse and the total. So the total is actually a combination of the transverse and the longitudinal. But it turns out that the longitudinal had no error. It was all showing up in the transverse, which finds its way into the total. Once you run it through the inverse of that sinusoidal filter, the error completely disappears. Problem fixed. The issue was, it's actually magnified by planes that fly faster. So we originally thought this was going to be a problem on the slow-moving turboprops. It turns out it's an even bigger problem on jets. And the reason why is when you observe wind, you observe it over a period of time, like say 10-second interval. You can't observe it instantly because the plane's jittery, there's all sorts of turbulence, data's really noisy. But if you average it out over a finite amount of time, you'll get a decent wind observation. But the issue is, if I say, let's take a 10-second average, and I'm comparing two different planes. Let's say this plane is a Saab 340 turboprop, and this is a jet. The jet's flying twice as fast as the turboprop. It's going to cover twice the distance as the turboprop in the same amount of time. And if this is the angular error, you can see if these two planes had identical angular error, the error of the jet is going to be essentially twice as large if it's flying twice as fast, because it covers the ground track is that much greater. So a lot of things that we were struggling with were, do we make the sampling time shorter? Well, the data gets noisier. The easy thing to do is just implement this correction. So we actually stumbled across some additional problems because we spent all this time trying to figure out how to correct wind direction of aircraft data. And then it turns out that in the data assimilation systems, in every model, I don't care whether you're using WRF or GFS or the European Center or even MM5 or whatever, they all use.
I'm not sure anything we know what MM5 is.
For the barotropic model.
Some me, John, and you.
They assimilate wind in the form of U and V vector components. Here's the problem. When a plane observes direction and speed by two different observing systems, you have a unique error associated with direction. You have a unique error associated with speed. So you have an angular direction and a value of meters per second in speed. If you use that speed and direction to derive a U and V wind vector components, then you have both directional and speed error embedded in your U and V components. And you don't know in the U and V component error how much of it came from speed or how much of it came from direction. And if I give you a set of U and V components, you can't back that number out. And so this is an issue because if you actually look here, if we take wind speed, as wind speed increases, the wind speed error, which are these, actually increases, while the directional error decreases. And if you think about it intuitively, it kind of makes sense because slow-moving wind kind of meanders around. Fast-moving wind is usually more dictated by stronger pressure gradients, and it's faster. It's going to have a more direct flow. So the errors from the speed and the errors from the direction are inverse. And if you convert these to U and V vectors, you lose the ability to quality control based on speed or direction. And in the model, you have a process where it compares the observation to the first guess or the background. And if it exceeds a certain amount, it throws out the observation. The question is the model throwing out good observations, or is it actually assimilating bad observations? Our hypothesis was if we use speed and direction instead of U and V vector components, we can actually improve the selection and rejection rate in the model. And I'll give you an idea of how this process works. So this is an idealized example of how you generate an analysis increment in a model. So you have your U and V observations. So let's just say this is what the aircraft data observed. This is the wind vector and U and V components. And then over here, we've got the first guess or the background. So this is what the model thinks. And this is what the observation is. And you're supposed to come up with some sort of blend of this. And so for this particular idealized test, we said, let's weight the observations half and weight the background half. So they both get equal weight, essentially, 50-50. So you should end up with something halfway in between. And of course, you do end up with something halfway in between. So this component is halfway between these two, and this component is halfway between these two. But what's the problem? The magnitude of this vector is shorter than both of these. It doesn't make any sense. If you use speed and direction, so here we have the angular difference between these two. The direction is halfway between them. And the speed magnitude is halfway between them. So this actually, in theory, makes more sense. But, you know, that's theory. We have to test it in the model because a lot of times theory doesn't work in a model. So to give you an idea, if we start, this is overlaying both of these together. If these are the observations and this is the first guess, using these two different data assimilation methods, these are the two different analysis vectors we come up with. Quite different. So here's two idealized cases. We've got case 1 and case 2. So let's just say for the purposes of this thought experiment, the air is 2 meters per second. So in for example, WRF, there's this error lookup table. Every observing system has its own set of errors. And it may be by pressure level or whatever. And you can enter any number you want in there. So let's just say it's 2 meters per second. And let's say the rejection threshold is an observation minus background that's 5 times the assigned error. So if the O and B is 10 or greater, the model throws out the observation, just ignores it. So we've got this first case, case 1. We've got your observation and your first guess. 180 degrees opposite of each other. Yet if you actually consider the difference between these two in either the V or the U, if that magnitude is less than 10, this gets assimilated into the model. But if you use the speed and direction method, it gets rejected. Now I would call this a bad observation. In case 2, we've got 2 scenarios here. They're fairly similar. So we've got an observation and a first guess. And the difference could be, you know, let's just say the difference is greater than 10, the speed difference is. But the angle here is 60, the angle here is 15. So this would be an observation that would be worth assimilating. And this one would be worth assimilating too. The problem is, if this difference in this particular case, or say this difference in this particular case, is greater than 10, this gets rejected by the U and V method, but the speed and direction method assimilates it. So if we think about these two cases, so here we have lower speeds and higher angular differences. That's typically going to occur lower in the atmosphere where you have a lot more variability in wind direction, but the wind's not going as fast. And up here, we have higher wind speeds and lower angular differences. This would typically occur higher in the atmosphere where the atmosphere is more homogeneous and the air flows a lot stronger. And so just to sort of test whether this worked or not, we actually plotted the number of observations assimilated using 2 different types of runs. So here, these 2 dotted runs, these are the U and V runs. And this solid line is the wind using speed and direction. And you can actually see that in down here, more of the U and V were assimilated. And up here, the opposite's true. More of the U and V were rejected. And the solid line sort of crosses the dotted line somewhere around 500 millivolts. So this is case 1, and this is case 2 from that previous idealized example using a real-world model and forecast. So we're actually using this version. There's as far as the, I think maybe WRF 3.1, there's now an option in there to select this type of wind data assimilation versus U and V vector components. You can test it yourself. We're actually using methods like this in most of our modeling systems. And actually, if you want to read more about this, the paper that we wrote on it's in Telus. Not high on the radar in the U.S. Met community, but this definitely got the attention of the European Center, who's actually using some of this style, speed, and direction for atmospheric motion vectors from satellites, as well as aircraft data. So we'll shift gears here a little bit and go back to the ice detector. I've got a couple of case reports that I put together for the NTSB. This takes us back to using raw data for forecasting purposes. So I don't know if you remember this, but there was a crash in Buffalo from a Q400 on Colgan Air. We didn't have a sensor on that plane, but we had a sensor on the plane in front of it and on the plane behind it. And what you see here, this line is an approaching plane. So this plane descending right here, it's the same plot, just that one has lines. It's above, each one of these is an observation. This is a positive icing observation. Positive ice, positive ice. The hollow triangle means the heater's activated. And what we see here is when this plane does this entire U-turn, the heater just stays on. And what that tells us is the accretion rate is matching the heater's capacity to de-ice the probe. It's not necessarily conditions you can't fly in. It would just mean there's a different set of procedures and protocol that you would want to be operating under. And if you weren't operating under that, you're going to have all sorts of issues, primarily stalling the plane because the weight and the airflow dynamics change on the wings. So back to some fun SQTs. So these are the profiles from the plane. This is the one from the plane in front of it. This is the one from the plane behind it. And you can see here, it might be kind of hard to see, here's the 0C line, and here's the -10 line. And this is essentially a saturated atmosphere that goes up to about 6,500 feet. I only know this because I've seen the high-resolution version of this slide. Down here, same thing, running from about -1 to probably -5, from about 3,200 feet to the surface. So between the plane in front and the plane behind, that layer of icing had shrunk, but you're still in a zone of what they call supercooled liquid. So this is liquid water at sub-zero temperature, which basically means if anything touches it, it'll instantly solidify. In fact, if you have really good purified water, you could do that in your freezer. Just take a bottle of purified water and stick it in your freezer and don't touch it, and pull it out and then flick it, and the whole thing will turn to ices. If it doesn't, then your water's not pure enough. So this, these are actually, yeah. So you can see the plane tracks on the photographs up there. So I've got a few minutes left, but I wanted to add time for questions. But I do want to talk about our global model since that seems to have got a lot of people's attention. But before that, we get to the fun times of actually drilling holes in planes. Flying used to make me nervous before I actually understood how much stuff went into testing. To get certified to install anything on a plane, the testing process is like a decade-long procedure. There's so many tests and so much redundancy that I'm convinced absolutely nothing can go wrong. Only time you ever see plane incidents are when the pilots actually fight the computers because the plane knows how to fly itself better than the pilot probably does. We're doing an install here, and the directions were the white wire is the hot one. So we'll see. By process of elimination, eventually find it. So this is actually what happens. We break out the drill and drill a hole in the plane. So when you're boarding a plane, you may actually see the probe sticking out, because if you're boarding, look down. Usually when you're going over the jetway, you can look down, and there's always like 2 or 3 probes sticking out. Well, one of them is going to look more like a foil, like a wing. That would be a TAMDAR plane. So this is Bill Moninger. He's the one who wrote that paper that uncovered the wind air. This is Stan Benjamin, who's basically the godfather of NWP in this country. He wrote the Ruck model from scratch by himself. Okay, so I put in a couple of slides on our NWP program, including our global model. So we do run a version of the GFS. We've been running it since 2007. It's so highly modified now, I don't think INSEP would recognize it. We've coupled a 4D ensemble variational data assimilation package to it. To do that, we actually have to run the 80-member ensemble along with it. We only need to run it out a few hours for the purposes of the data assimilation process, but we do run the ensemble all the way out to 240 anyway, because people want to see probabilistic forecasting now. We do have a major upgrade coming in a few months. We've been parallel testing a non-hydrostatic 9-kilometer version, which we'll probably switch to if everything goes as planned. The skill scores were impressive. It took us from 2007 until about 1.5 years ago to get out in front of INSEP's GFS. And then during last hurricane season, we actually caught up to the European Center for a while. And then the European Center did an upgrade in March, a few weeks ago, and now they're back in front of everybody. So INSEP has an upgrade coming next month. They think it'll close the gap to us. It might, I don't know. We've got an upgrade coming too this summer, so we're hoping to close the gap on the European Center and open up the gap again on INSEP. But you know, it's fun, but we share information back and forth. A lot of our code is originally from the GFS. There's stuff like the observation operators for TAMDAR data that we designed and wrote and funded ourselves, and then shared that back with the community. So you can download the data assimilation package for TAMDAR data. It's part of WARP. We've written one for the GFS. If you really want to run the GFS, you can do that too. And we use this GFS to actually power our regional models. So we still run high-resolution regional models. They're all WARP-based. They use a 40-bar data assimilation. We run them over different regions, primarily set up to serve the aviation community. And then we run a tropical WARF, but we'll probably turn it off because, as I'll show you in a second, our GFS destroyed our version of the tropical WARF so bad it's not even worth looking at. The global model, now that the resolution of the global model is so high, there's almost really no point in running a limited area tropical model. For the quality control, we still use RTF DDA WARF, which is not variational. It's basically odds nudging, but if you cycle it rapidly, you can get essentially the same forecast. We use this for generating those plots with statistics that I showed earlier. We also run a global GTG, which is similar to NCAR AWC's turbulence model, except we've tuned it to TAMDAR anti-dissipation rate instead of PIREPs, which are just some pilot saying he thinks the plane's shaking. It's so subjective, because if you have a pilot that's been flying for 30 years and a pilot that's been flying for 6 months, they're going to tell you 2 different things. And then if you have a pilot that's in a 777 versus an ERJ, they're going to sense 2 different things.
I got a question on that, since some of the people in here actually know about this. We talked about it. What are your algorithms in GTG? You got 19. That's more than Bob uses.
So there's some overlap here.
Yeah.
So we split it into upper and lower atmospheres,
right.
and so there's a mix. So some of these are the same, but they're lower and higher. So there's a split there. And actually, yeah, one of our forecasters, Alan Huffman, was part of the group that wrote the NCSU algorithm in the suite. And then we also run an icing potential model, which is a lot like the SIP, except again it uses SAMDAR data as well. And I think probably the biggest question was, how do you run the GFS? What kind of computing resources do you have? So our GFS, we actually run several different versions of the deterministic model. Our current operational one is the 13 kilometer. Like I said, we're running a high resolution version in parallel. The operational one we run, and it's redundant, so we run two identical parallel versions of this. This is just for the purposes of when you're supporting the aviation community. If you have an outage and they have planes in the air, they're very unhappy. So everything's fully redundant. The production system is 11,000 cores, which is smaller than INCEP's system, but INCEP's system is probably 80% of their usage is actually climate models, and then the HERC. The GFS on the INCEP system actually doesn't take up that much space.
Can you, well, let me make a pitch. If you take data assimilation with me next spring, a lot of this will make sense. If you haven't heard it already, can you say kind of simply the difference in your data assimilation versus what's being done with GFS at NCEP right now? So that's I guess kind of at the crux here, isn't it?
Yeah, so right now NCEP is using a 3D NVAR technique. So the difference is basically the fourth dimension. At some point in the near future, they're going to upgrade to a 4D NVAR. There's a lot of other different things we're doing, you know, from sea surface temperature to different satellite schemes, GPS RO, observation operators, the whole aircraft data thing I was talking about. All that stuff gets fit into the data assimilation package. But the big difference is the 3D versus 4D.
Okay.
And the European Center actually uses 4D variation. So that's actually what we're using here. So the difference between the NVAR and the true variational is the true variational has what they call tangent linear and adjoint, which is basically you're running the model in reverse for your process, is extremely computationally expensive. So that's one reason why this 4D NVAR was really appealing to us, because we don't really care for our customers. Day 15 forecast doesn't really matter. It's the aviation community. What they'd really like to see is, can we do a rapid cycling version of this 4D NVAR? Can we cycle it every 3 hours? You know, so computational efficiency is extremely important here.
Okay. So I'm going to guess a little bit of that in other people's heads. Okay, the fourth dimension is time. That's the key here. And so what they're doing is, through time, they're changing essentially their statistics are not frozen in time, but their whole statistics thing updates and updates. That's a huge difference between the 3D and the 4D.
Right. So a crude way to explain it is say your analysis time is at t equals 0, and this is your t equals 0 could be, I don't know, 0z. And you have all these observations collected. Typically, an observation, what we call a binning window period, is maybe several hours prior to t equals z, and then actually some time past it. So maybe, you know, an hour, 30, 40 minutes past t equals 0. We take all those observations, and they all have a 3-dimensional position and a 4th dimension of time. And you try to crunch them into your best guess of what the atmosphere is at t equals 0. Now, a 3-dimensional assimilation technique is smart, at least is smart enough to understand that this observation over here was 4 hours away. So it can't correct for its misplacement in space-time. So it devalues the impact. And so if you collect all your observations right around the synoptic time, this 3D bar is not bad. If you're using observations like satellite, you know, and aircraft data, which is all the time, you really need to have full weight of the 4th dimension. So with the 4D, you're actually taking the full weight of every observation because you don't have to devalue it because you're putting it into the analysis at its proper space-time. And I know it'd almost be easier to look at the math.
So Neil, we probably have got about 5 more minutes, and I
Yeah.
do want to have a couple of questions from the students as well. So
Yeah, I've got 2 more slides.
okay.
So this was the plot that got everybody's attention. So the black line here is the observed track. The blue line here is our global model track. This is Hurricane Joaquin. The pink model here is the European Center track. The green model is the INCEPT GFS. These other 2 models were limited area models initialized off the GFS. And of course, they went for the loop-de-loop, hook, line, and sinker. And the Hurricane Center manual track, which basically thought the European Center was out to lunch, and they went all in with the GFS because they've got 3 models here that agree with each other. Problem is these 2 are initialized off this one, so how different can they really be? We thought we were an outlier, except the fact that we agreed with the European Center, and the European Center had pretty good skill scores. So this was just one particular run. If we actually looked at every single run that included a forecast track, these are the errors, minus ours. So obviously ours minus ours is the blue line. The ECMWF is the green, so they actually were outperforming us on track in the short term, and then we sort of edged them out in the long term. But essentially, we were neck and neck. And then down here, you see the other, the GFS, HWRF, and the GFDL. These are all runs that included, I think it was like 4 days worth. So to give you an idea of what those look like, here's the official guidance, here's the GFS, here's the HWRF, and there's all the tracks from our global model. So yeah, I got accused of cherry picking that 18Z run because it had this crazy stuff over in the mountains, which I thought was funny, but this is what really happened. So we verify our models a lot of different ways. If you want to see what the recent anomaly correlation scores are, this is after the European Center's March upgrade. So just about the time we caught them.
Yeah, could you take maybe 30 seconds? Because this is a very common way of verifying model scores. Explain to them what that is.
Right. So you're essentially trying to determine how well atmospheric anomalies correlate, basically. So what you do, the way you calculate this stuff is you would say, let's say, for example, we've got a forecast. It goes out 10 days. And on the 10th day, you have a known climatology for that day, okay? And so that's, whatever the 500 millibar heights are for day 10's date in your climatology. And then you take the forecast for the day 10, and you can subtract off the climatology. And that's going to give you the divergence from climatology, i.e. the anomalies. And then what you can do is you wait 10 days, and then you do that again with the analysis, or whatever, short-term, let's say your t equals 0 analysis. You can subtract that, this climatology off that, and then you end up with the anomalies in the atmosphere that are actually really there. And then you try to determine how well did your prediction of those anomalies match what was really observed. And of course, a perfect correlation would be 1. And this is day 10. Day 10 statistics tend to waffle around, 0.4, 0.5. So after the European Center upgrade, their anomaly correlation scores as of the last few weeks have been around 4.8, 4.87. Ours are running around 0.47. 0.487. We're at 0.47. GFS is 0.44. So the European Center actually had a significant boost. They made a major, major upgrade. I mean, they switched a lot of stuff in this, and they took off. But I think we'll catch it. But the important thing here is there's a lot of different ways to verify the model. So the last slide I have here is just radio sign verification in 12 hours, which is not really exciting to look at a 12-hour forecast from a global model if it goes out 10 days. But this actually just looks at the difference between U and V wind, mixing ratio, and temperature. And you can see us versus GFS. Numbers really don't look that big, but again, when you put them in terms of percentage, 15 to 20% improvement. I suspect INCEP's upgrade is going to close this gap. So that's all I have.
One or two questions. One quick question I'm going to ask, and I want to hear. What did you say is one of the most important skills you guys are still looking for in hiring?
Fortran. Don't laugh. A lot of our global model code is Fortran 77. Probably to prepare yourself, at least for the industry that I work in, computer programming and a really strong math background. You know, it's nice if you know Cumulus versus Stratus or Cirrus or whatever, but it's really applied math and programming skills, particularly Fortran, which it might be tricky.
So if you got a moment to squeeze a Fortran class into your some of your younger students, I would recommend it because this emerging private sector is going to be where some jobs are. I mean, there are going to be other companies I suspect like Panasonic that are popping up, and there already are some.
Yeah.
And these models are still really important.
Yeah, and we've got open searches looking for people who know Fortran, and one of our current Fortran programmers we had to contract out of retirement. You know, so it's not easy to find that anymore because it's not the cool cutting edge language, but it's still the best language that I know of for big number crunching and parallel processing.
Maybe one more question from a student. Anybody got a question? I know you guys, some of you got to head off to Astrophysics or whatever. Any other questions? John?
I do have a question. It's a nonlinear question, but I'll try to linearize it. How much of your improvement is because you're using the wonderful additional data, and how much of it is your better data assimilation?
I can't answer that.
I know, it's
yeah. I suspect it's obviously some type of combination of both. But in the global model, my sense is we've done so many more tweaks from the physics, the microphysics, all this other stuff.
But it's the other stuff too. You've also improved the whole.
Yeah.
Okay. So there's that too.
Yeah, there's a lot of other stuff in addition to the aircraft data.
Okay.
But we don't have a control version.
No,
So let's stop it. I wanted to make sure that Taylor Sorrell is the person that you would be emailing, and her dad's actually works for Panasonic. So thanks, Taylor, for sort of reaching out. Thank you, Neil, for coming.
Twitter question.
Oh, we have one question off Twitter. Hi, Twitter world. We do have some questions. I forgot we did have people screaming. So let's quickly ask that question.
This question's for
Jordan McLeod, one of our former students, is at UNC now.
Okay, so the question is, are there any plans to make the Panasonic global model available to public or will it remain?
We're discussing that right now. The issue is we can't make our gridded output files available to the public because the cycle generates about 4 terabytes. Okay. And if we opened an FTP server for a free-for-all, people try to download 4 terabytes. 1, it would jam our system. 2, they would never get the output, at least in even remotely real time. We probably will make some products available, maybe images of 500 millibar heights or something, and release those on a time delay, because, as a business, we have to make money on what we've invested to develop, and there's a lot of utility in research. So one of the things we do is we set up research-only license agreements for universities for the data and the feed. So, NC State, University of Maryland, OU, UW, Cliff Mass's group has been assimilating TAMDAR data in their model for a while. For research-only purposes, you can get a real-time TAMDAR feed. You may or may not be able to get a global model output feed, but certainly on a time lag basis, maybe 48-hour delay or something will make some stuff available.
Very good. And we'll pay you extra. We'll use it for our weather challenge team, and we'll destroy everybody.
Yeah. All right. Thank you, everybody. I know you guys got to get to class. Some of you do. If you don't, feel free to come up. Thank you guys out there. last guy that asked the question, we're actually